and them to be altered while they're sent. There might be a microwave standing right next to it, and it will just be total crap, whatever the hardware is receiving. So we don't want that. The third thing is a very big point for us is we need guaranteed delivery. Whenever a fuzzer sends out a packet, we want to make sure that this one packet makes its way into the device driver. There's no need for this packet if it's dropped at the hardware, and we don't know. We might be sending hours and hours of data and it never reaches our target. So we need guaranteed delivery, and like I said before, we want additional advanced target monitoring in our new approach. And the solution was to move the target, the fuzz target, into a virtual environment, into a virtual machine. So why do we do this, and what are the advantages of doing so? Well, the first thing we have is our virtual wireless device, which is written in software. We have a virtual machine that's emulating a piece of hardware, and to be honest, this piece of hardware on our laptop is nothing else than a black box. We send something in, and we hope that something's coming out of it, but we have no idea what's going on. So since this virtual wireless device is a piece of software, we can use high-level inter-process communication to do the transmission, the injecting, and so on of our data. So basically what we do, when a fuzzer wants to inject a packet, it just tells our wireless device, please inject this using shared memory, and then afterwards uses a set of semaphores to say, okay, what did you do with the packet? Did you pass it on to the network stack, or did you drop it? And if you drop it, could you please tell me why? Was there, maybe, did you have wrong frequency? Was there no memory left in the device driver? Or was it a corrupt packet or something? So we can really query our device and find out what happened to our packet. The third we have on there is that we have a virtual CPU. There's nothing better than that. We can hold the execution of this virtual CPU at any time that we want. So when we inject the packet, we simply tell the fuzzer, or other way, if we see that our virtual environment wants to send out a wireless packet, we simply stop execution of the virtual machine. Then the fuzzer can go ahead, take the packet, disassemble it, look what's in there, and say, okay, I want to reply to that, that looks cool. Generate whatever is necessary, inject the reply packet, and then continue the execution of the virtual machine. So for the simulated system, there's not one single loop of execution, not even 1 microsecond between the outgoing frame and the incoming reply to the frame. So we have even less timing distance between the outgoing and the incoming frame than in real time. So we really have no timing constraints with that. And the fourth thing we have on there is guest OS monitoring. Whatever we do with casual fuzzing of wireless device drivers, we can do the same thing in a virtual machine. We can have somebody sit in front of the virtual machine and just wait for it to crash. However, we have other things we can do on a real low level. We can, for example, trigger certain events in the virtual machine. We can trigger restarts. We can tell our fuzzer, whoops, system just restarted, tell our fuzzers about it. We can hook our graphic cards, it's virtual, it's all software. So we can take a look at some pixel and see, whoa, it just turned blue. Look at the whole screen, well, everything's blue, oh, there's a blue screen of death. We can also really just simply pipe out the text that's being sent to the graphic cards and see, well, there's a print K, there's a kernel panic. That's obviously a system crash. So we can really hook system events and tell a fuzzer about it. We can go even further and install hardware breakpoints into well-known code areas. For example, we can install a hardware breakpoint into well-known code areas like the Windows blue screen of death. And before the system even crashes, we can notify our fuzzer and maybe even debug the system that's crashing. So we have a lot of additional opportunities with our new approach with a target in a virtual machine. So we have drastically simplified the complexity not only of writing fuzzers, but also of the fuzzing process itself. So our solution, like I said, it's based on a virtual machine, and our implementation is based on Fabrice Belas Kuemu, which is an open source software, open source virtual machine, and just like any other hardware that you can use to be simulated inside the virtual machine, we have our virtual device as an optional Ethernet card that you can add during nice tune. That you can add during startup with command line options. And during the implementation, we also said, well, we have to stick to a very modular design. We said, well, this virtual device, we shouldn't really make it a fuzzer. We want to have something generic. So we said we have the virtual device only responsible of doing two things. The first thing is synchronize the incoming and outgoing queues of the device driver with a shared memory that other modules can connect to and inject packets and look at outgoing packets. And we also have the virtual device take care of notifying those modules that connect to the shared memory. So we can really tell them, well, go ahead and tell me about system restarts, about injected, about outgoing frames, and so on. On the next slide, I have a short picture of our system overview. On the left, you can see we have the virtual machine QEMU. We have an operating system running inside. It's either Windows, Linux, or Mac. We only tested on Windows and Linux, but there shouldn't be a big problem porting it to Mac. You have a virtual CPU inside. We have virtual memory. We might have optional Ethernet cards or just any hardware that we want. And we also have what we call 802.11 fuzzer, which is exactly an Ethernet card. It has the shared memory that outstanding modules can connect to and interact with. And down here you can see, well, it identifies itself as a Theros communication 802.11 NIC revision 1, and you will see that in a demonstration later. On the right you have modules that connect to the virtual device. We have two basic modules called dumper and listener. They do nothing else than really look at the outgoing packets and just either store them on disk or just print them out in a somewhat human readable form. Then we have the injector, which does nothing else than inject arbitrary data into the virtual device. And we have what we call stateless fuzzer module. The stateless fuzzer is basically nothing else than what was presented at Black Hat Europe this year. Stateless in this sense only means that it stays in state 1, so it does not go into authentication, association, or any encryption or any data at all. So this is very basic. However, on those two modules, or two types of modules, we have developed access point module and a stateful fuzzer module that we're going to deal with on the next slides. So the access point module, it's really nothing else than what the name suggests. It's a software version of a real access point. Actually, it's simulating my Cisco router I have standing at home. It does everything a real access point has to do. It sends out beacon frames, it responds to probe requests, it responds to authentication and to association requests. And we also have a minimal implementation of the ICMP protocol inside the access point, just to make sure that higher level protocols work as well. And what turned out during the development, but also during the fuzzing process, that it's very handy to have full logging of every single frame that goes in and comes out of the virtual device. So we have full logging of the 802.11 traffic. But as words are always hard to explain something, we're going to switch to our first demonstration now. I'm starting up my tool. I'm just going to explain what I did afterwards. Whoops. I had to restart my system before. Okay, to show you what I did, I hope you can read it. I'll just make it a little bigger, this one too. Okay, up here it's a script that I started QEMU with. I invoke QEMU with a image I have on my local hard drive, and I emulate two network cards. The first one is called of type model RTL 8139. It's a basic network card, standard QEMU implementation. And the second one we added was of type WLAN fuzzer, and it's simulating an HP W400 device. You can see that on there. Make it a little bigger. Oh, still can't see, it doesn't matter. I have a virtual device set up, and I've also started the listener module over here, so it's going to show us what's going on inside the virtual machine. So I have then resumed a snapshot so I can skip the Windows boot up process, because as we saw with Jeff Moss, it might take hours. And just can continue execution, so I can switch to my virtual machine. And as you can see down here in my hardware manager, there's a RTL 8139 standard network card, and there's also an HP W400 wireless network card that I can use. Okay, there you go. So if I now take my wireless connection manager, I can scan for networks, and what I can see in my listener down out here, I can see that there are constantly frames coming out of the virtual machine. It's somewhat human readable, but on the bottom you can see that it's management frames coming out, which are probe requests. And on the top you see that the frequency is changing all the time. So that's basically just what I said at the beginning. Windows XP is sending out probe requests to find out everything it can about available networks in the area. Obviously I only started my listener module, that's why it didn't find anything. But what I can do now is just start my access point. And I'm also starting a monitor over here that will just show us a little bit about what's going on. So inside the access point I can tell it to say, I can give it some SSID I want to be announced, say, yeah, Val 7 sounds good. Say, go ahead, start simulating the network, and in my monitor I can see, okay, it's starting to inject beacons, regular intervals. So if I turn back to my virtual machine, I can say, please rescan. And voila, you see, there's a new wireless network connection. So just to have a little fun with it, let's go ahead and connect. Say, yeah, we know it's not secure, but go ahead. You see there's something going on in the background, and you see it's getting an IP address down there, and we have a perfect connection. So just give it a few seconds to start the logging. Okay, so I can go up there where we started the logging. You can see that after injecting some beacons, we suddenly received a packet while we were not authenticated, and it turned out to be an authentication. So we simply replied to that packet, turned into state 2, authenticated, received another packet which turned out to be an association request, replied to that packet, and suddenly we were in state 3 where we can use higher level protocols. Then there were packets coming out which turned out to be not management frames but data frames carrying higher level protocols, and they turned out to be ARP requests for 192.168.3.3, which is the static IP address inside my virtual machine. So Windows XP is sending out an ARP request just to make sure that it's using a unique IP address. Afterwards there's a lot of IP traffic, which is basically nothing else than Windows trying to search for available services in the local network. We obviously don't offer them, so we simply drop those IP packets. But like I said before, to test higher level protocols, we have an ICMP implementation. So I can go ahead and say, show my ARP cache, and obviously there's nothing in there. But I can ping my access point because it's listening on the IP address 0.3.1. Just go ahead and we see we get a reply. And the background, in my logging, I see there's a data packet coming out. It turns out to be an ARP request for 0.3.1. That's me, so I reply to the ARP request. And afterwards, there's a data packet coming out, which is an IP, an ICMP packet, which I can reply as well. So we see we have full control over the network connection. We don't have timing difficulties. It's really easy to do the communication with that. And having said that, let's just switch back to the slides. So the next module I want to talk about is the stateful fuzzer module. Unlike other fuzzers that has been published, we do stateful fuzzing, so we go into state 2, we go into state 3, and do everything we can there. And the fuzzer module really behaves like the access point module, but we can tell it to replace single packets with a fast version of it. So we can really say, fuzzer module, go ahead, act like an access point, and as soon as we receive an authentication, we want to reply with a fast packet. So we can really pick out single packets and fuzz these. And we will also show this module in a second. But I'll just sum up the results of the fuzzing we did. I showed you we developed a framework for fuzzing wireless device drivers using the virtual machine QEMU. However, we can not only use it for fuzzing, we can use it for just about anything. We can use it to test new wireless protocols. We can use it to test new device drivers. We can do anything we want to it, or we can just be cool and have a wireless connection on our virtual machine. And we have, with a simple fuzzer, we have not only stateless but also stateful fuzzing in all 3 states of the communication handshake in management mode, but it can be extended to ad hoc mode and so on of wireless communication. It's not a problem. And to see if our fuzzer really works, we have taken an old version of the Mad Wi-Fi driver for Linux